Okay, so one announcement today. Um, Before I forget, I want to knock this out first. Um, so I mentioned at the beginning of the course that we were switching from the Examity test proctoring system to the ProctorU test proctoring system. And I mentioned that we were kind of still working on some technical details. Well, unfortunately, the faculty member that I was working with and I um, long story short, ProctorU does not work very well with some of our math systems. And we are not able to, we think we found a hack, but we're not able to actually confirm that the hack will actually work, just the way that our accounts are set up. They're not student accounts. So long story short, our exams will not use ProctorU. Um, the exams will still be set up the same way. They'll still be given over WebAssign, still be the same material, same dates, and all of that. You can check the syllabus and course schedule for all of that information. But the main difference will be that the exams will not be proctored. Um, this being a developmental course, Math 90, really the purpose of the course is to help you succeed in, say, Math 108 or Math 106, or one of the 100 level maths that you need for your degree. So I would still strongly recommend adhering to all of the exam policies, even if there's not proctoring. Not just for uh, not just for the integrity of of kind of your feeling about your grade and knowing that you earned the grade, but also for setting yourself up for a good, 100 level class. So if if you kind of take the easy way out on a Math 90 exam, it's going to be tempting to do that in a future course, and we should have things, I think, ready to go and proctoring back online, um, by the summer semester, hopefully. So no ProctorU for any of the exams in the course, but I would recommend still just basically taking them as though proctoring was there. The plan for today is to cover 2.7 on solving linear inequalities. And the quote of the day today is from chess grandmaster Daniel Naroditsky. He used to post a lot on YouTube. I haven't seen a whole lot on him from him on YouTube recently, but I think maybe he's streaming on Twitch now or something. Um, but he's fun to watch. He's entertaining. He's a history buff, so younger guy, but a history buff, which is, you know, not all that common. Um, but he's, his general commentary is usually interesting, and then of course he's very good at chess. Um, but the quote of the day comes from him: "Prosecute the advantage." So to prosecute, we usually use that word these days in the legal sense, but it really just means to kind of move forward with intent, something like that. Uh, and his point is, if you have an advantage, press that advantage. And I think this is kind of expanding on this idea a little bit. There's a difference between abstract and concrete advantages. If you take chess, for instance, one of the kind of challenges of chess is that at the beginning of the game, all of your good pieces are hidden behind pawns, and they're kind of like, it's kind of awkward to get them out from behind the pawns and be able to use them to attack your opponent. So, um, and say the opening of the game, maybe you get a couple of your pieces out faster than your opponent. Maybe you have three pieces out, your opponent only has one out. Maybe your opponent brought out their queen early and you're able to hit their queen with, say, a knight and a bishop, and they had to keep moving their queen around while you're getting pieces out from behind your pawns. That's kind of an abstract advantage, right? It's fleeting. It's if you fall asleep at the switch for a couple moves, your opponent gets a couple pieces out, they've caught up, that advantage has disappeared. You didn't prosecute that advantage. It was there for a little while, it disappeared. Consider that in relation to, say, a concrete advantage where I have three pieces out, my opponent has one piece out. I develop an attack on that basis because their one piece can't really defend against my three pieces, and I win, say, their light squared bishop. Well, for the rest of the game, they don't have a light squared bishop. That's a concrete advantage. I've prosecuted my advantage. I've converted, say, an abstract advantage into a concrete one. uh, what does this look like for students? Probably the most, I think this applies to a lot of areas in life, but probably the most obvious example for students is a degree, right? Most of you uh, are taking courses at CCAC with the goal of working toward a degree, with the goal of establishing a career that you find, purposeful, that brings financial independence, that, that does something that you enjoy doing, etc. Well, that degree, I mean, a degree is a huge accomplishment. I'm not taking anything away from that, but it's an abstract advantage. That degree doesn't get you that career or that purposeful work. That degree gets you some doors open, right? But you have to prosecute that advantage. You have to take that degree and you have to, a few months before you graduate and a few months after you graduate, be going to job fairs, maybe shadowing some folks in businesses you'd like to work for, getting them to know your name, getting to know, what's the hiring manager's name, what are some folks that you want to network with there to let them know when you apply. Right? You have to really press forward with that advantage, that degree, to turn it into a career or a lifestyle that you desire. So I think that's a good example of this. And just kind of in general, you know, life is going to tend to be a little more successful if you try to play your hand towards your natural advantages and away from your natural disadvantages, while also shoring up your disadvantages. So if there's an area that you're a little bit weak on, a particular subject or whatever it may be, like I'm never going to try to be an NBA player. I'm just, not tall enough, not built for that. But you know, math worked well for me, so I kind of went this direction. But that doesn't mean I shouldn't, exercise and try to be a little more healthy, right? So play your hand kind of towards your advantages while working to shore up weaknesses. So that is the thought for today. Okay, so we've worked through several sections, I suppose, in chapter 2, but at least the last couple sections, we developed this idea of how to solve a general linear equation. And basically the strategy was, well, first, clear fractions or decimals. I suppose that's step 0, we called it. And then get ourselves into ax plus b equals cx plus d by just simplifying, combining like terms and so on. And then we isolate the variable term, we isolate the variable itself, and then we check. So what we're looking at here is solving linear inequalities. I suppose I did need that space I just got rid of. Solving linear inequalities, we're still looking at most generally ax plus b related to cx plus d. Now, when we had an equal sign here, remember we thought of that as, well, that's like the worst scales anybody's ever drawn, but we thought of that as meaning that we have scales that balance, right? So we have the same amount of stuff on the left side as the right side. If I have an inequality, maybe I have something like this, ax plus b less than cx plus d. Well, that means that my scales are unbalanced. That means that my left-hand side is lighter than the right-hand side. So instead of being equal, instead of being straight across, my left-hand side is actually going to be lighter than the right-hand side. I have maybe 1 block on the left, but 2 on the right. That's 2 blocks over there. I'm not drawing my scales nearly as carefully as I did in the initial illustration. But this is the idea of an inequality. We still have our 2 expressions. We're still making a claim about how these 2 expressions are related. But we're not claiming that these 2 expressions represent the exact same quantity. We're claiming a relationship between them that's an inequality of some sort, that one of them is maybe bigger or smaller than the other one. And we have 4 different types of inequalities. Well, really 2, but they look like 4. We have strict inequality, strictly less than or strictly greater than, and we have non-strict inequality, less than or equal to, or greater than or equal to. So in other words, 3 is less than 5, but 5 is not less than 5. 3 is less than or equal to 5. Oops. And 5 is less than or equal to 5. So we change the strictness of the inequality depending on whether we want to allow that borderline case to be valid. Okay, so let's look at a couple examples here. Let's consider an inequality like this one, x bigger than 0, x bigger than or equal to 0, sorry. Let me zoom this in a little bit. Consider x bigger than or equal to 0. And at first glance, we'd almost say, like, this seems like it's solved, right? The equation example, equation equivalent would be something like x equals 0. And we basically said we kind of think of that as a solution. So x bigger than or equal to 0, we might call this something like an algebraic solution. It's a solution written in algebraic form. I can imagine different numbers I could substitute in. You know, if I substitute x 5 in for x, I'm going to write it this way. I don't want to write x equals 5 because I don't want to confuse the issue with the x greater than or equal to number. But if I swap 5 in for x, is 5 bigger or equal to 0? Yes, it is. If I swap -2 in for x, is -2 bigger or equal to 0? No, it's not. That's not a solution. If I swap 0 in for x, is 0 bigger than or equal to 0? Yes, it is. But with inequalities, I see that there are actually lots of solutions. 0 will be a solution because of the non-strict inequality. 5 is a solution because just of the structure of the inequality. But so is 6, or so is 12, or so is 15, or so is 3 halves, or pi over 2. There's lots of numbers that are solutions to this inequality. Sometimes it's nice to write it in an algebraic form like this. Sometimes that's the most useful way to write the answer. But there are two other ways that we could write the answer. We could write it as a graph or as an interval. So for a graph, we're going to draw our number line. So this is all real numbers. A point of interest is 0. That's what separates our solutions from our non-solutions. And then my solution set is all of the values of x, all of the potential inputs that are bigger than or equal to 0. And there's basically two ways to represent this. One way is by putting a dot at the boundary between the solutions and the non-solutions, drawing an arrow in the direction of the solutions. So x bigger than or 0, things like x equals 5. X equals 5 is over here. And then with this thought, I want to ask the question, what type of inequality is it? Do I want to include 0 or not? If I did not want to include 0, I'd leave it as an empty dot. But since I do want to include 0, I'm going to fill in this dot so that that boundary, that point at 0, is included in the solution. There's another common notation uh, for graphing solution sets. The arrow looks the same. So we still have an arrow pointing to the right. For instance, 5 is a solution. So we see that over there. And we might place a square bracket at the boundary between our solutions and non-solutions. So a dot or a square bracket, either that way or this way, if my solutions were off to the left, says include the boundary point. Whereas an open dot or an open parentheses instead of a square brackets says do not include the boundary point. So that's a graphical representation of the solution. Again, by hand, you can represent it either way. I think WebAssign tends to prefer the dot method, but you'll see it both ways. And then the other thing that we could use to represent our solution is an interval. So if I were to say, for instance, the interval from 1 to 2, I want to write down a notation that represents all of the numbers between 1 and 2. I could write an interval like this: square brackets 1 comma 2 and square brackets. And this would mean all of the numbers between 1 and 2, including the endpoints. Remember, these square brackets typically represent including the endpoints. If I wanted to represent all numbers, say, between 3 and 4, not including 3 and not including 4, I could use open parentheses 3 comma 4, close parentheses. I could also have a half open interval, like closed 5 to open 6. This would include any numbers between 5 and 6, 5.5, 5.7, anything like that. It would also include 5, so 5 would be represented here, but not 6. 6 has an open parentheses. That boundary point is left out. Now, something that I notice here is I want to represent all numbers bigger than or equal to 0. So I see my left boundary point is going to be 0. I do want to include it. Let me put a square brackets there. But what's my right boundary point? It's not a number like 2 or like 25. If I thought maybe it was 2, I could see that 5 is a solution. If I thought it was 25, well, 30 is a solution. Any number that I put here, I can go 1 unit further to the right and still have a solution, right? Even if I put 10 million here, 10 million and 1 is a solution. I have, practically speaking, no right endpoint, right? These arrows just kind of go off to the right forever. Well, we denote that idea, that concept, by using infinity. So I could represent my inequality algebraically by saying x greater than or equal to 0. I could represent it graphically with, say, one of these two graphs, or I could represent it in interval notation with this interval. Something to note is that infinity always gets an open parentheses, because they never really include infinity as a solution, right? Infinity is not actually a number. It's a little bit closer to something like a concept. So I can't like plug infinity in and ask, like, is it true that infinity is bigger than or equal to 0? That kind of like feels like it's true, but it's kind of an ill-posed question. It's a question that really doesn't make sense, because infinity is not a number and x is a placeholder for a number. So we always want to append an open parentheses to a plus or minus infinity. Now, if we look at this next one, we have our algebraic solution, we might call it. We're being basically handed the solution. This is our algebraic solution, x less than -5. So for instance, if I were to substitute in, say, 2 for x, is 2 less than -5? No. If I were to substitute in, say, -10 for x, is -10 less than -5? Yes, it is. if I were to substitute in -5, that boundary value for x is -5 less than, strictly less than -5. No, it's not. If I want to graph the inequality, a lot of times I'll put 0 on my number line just as kind of a placeholder. I see that -5 is to the left of 0. My solutions are those x's that are strictly less than -5, so to the left. I'll put an open dot here and an arrow pointing to the left this time. Because I have a strict inequality, because I do not want to include -5 as part of the solution set, I leave that dot empty. I don't fill it in. Up here, I filled it in because I had a non-strict inequality and I wanted to include the boundary point in my solutions. Down here, I leave the dot empty. If I filled it in, it would look like this. But I don't, oh, OneNote's trying to be too smart and it thinks that I'm scribbling things out. But if I filled it in, it would look like that. But I did not. There's a little line there, but that's just for the tick mark that's representing -5. It doesn't mean it's filled in. Or again, in a different notation, I could represent my solution this way. Up above, I used a square bracket, but here instead I will use an open parentheses. And I do want to make it, visually clear enough whether I'm using a square bracket or an open parentheses. And then going off to the left. So again, this open parentheses do not include the boundary point. So either of these ways would be valid ways to graph the inequality, graph the solution set. Or I could use an interval. I know the interval I'm interested in has a boundary point of -5. That's kind of where I switch between having solutions and not solutions. I know that that is a right bound. So what's my left bound? What's my lower bound? Well, actually, I keep going forever. I go off towards -infinity. I need to get the infinity, number one, having the right sign. It needs to be -infinity because we're going to the left. And number two, on the correct side of the -5. I wouldn't want to write, let me put a comma there. I wouldn't want to write -5, comma, -infinity. My -infinity should be on the left side, kind of like its location here. And then, so -infinity, I need an open parentheses there. And at -5, because it's a strict inequality, I don't want to include -5. I'll put an open parentheses there as well. So that's my interval notation for this solution. So all of our solutions to inequalities have three ways of representing them. Algebraically, like this up here with, an x and an inequality sign. Graphically with a number line and either a dot or a parentheses or bracket and an arrow. Or an interval notation, writing out an interval like this. Okay, so let's work on two exercises. Yeah, exactly. Yeah, so whatever is leftmost on the number line, if I have a number line like, A to B, and I'm looking at, the interval between those, let's say including those endpoints, then A goes to the left of B in the interval notation. Yep. So whatever's to the left, whatever's further negative on the number line is what goes to the left in the interval notation. And whatever's to the right in the number line goes to the right in the interval notation. Yep. Okay, so let's work on these two exercises. Um, take a few minutes each and write out the number line. I would actually say write out the number line, the graphical solution to the inequality, both different ways, using the dots and using the brackets, and also write out the interval notation. Be careful with your infinities and negative infinities. Which side are they on? Be careful with your number line. Which direction are the arrows pointing? Are you using filled in dots or open dots? Are you using square brackets or parentheses? Which way is everything pointing? So, take a couple minutes for each of these. I know that you probably could scratch out an answer really quickly in 30 seconds or something, but take about maybe 2 minutes each. Go through it carefully and diligently, and make sure you get all the details right. So let's come back in maybe 3.5 minutes or so and discuss these two. Okay, let's work through these two examples. So the first one, we want to graph and write an interval notation x less than or equal to 7. So for instance, numbers like 5 or 2 or -3 would be solutions. Numbers like 10 or 12 would not be solutions. And 7, right on that boundary between the solutions and non-solutions, because this is a non-strict inequality, it's a less than or equal to, 7 itself is a solution. So we draw a number line, we indicate where 7 is. We know that 7 is going to be a solution, so we either represent that boundary point with a dot or with a square bracket. Just two different ways to say the same thing. I'm writing them, both ways just so that we get used to seeing both notations. But in, a particular example on WebAssign or on an exam, you would use one notation or the other, just to be clear about that. So I have my boundary point at 7 indicated properly, either a closed dot or a square brackets. And then I know my solutions are to the left, right? Numbers like 5 or 0 or -2, say 5 or 0 or -2, are solutions where numbers like 10 or 12 are not. So I can use some test points to even check that my graph is correct. Does it seem like this graph represents that algebraic solution? And I think it does. And then my interval notation, I know that my solutions kind of point off to the left. If I tried to put a lower bound, if I said I think my solutions are like -1,000,000 to 7, we could go to -1,000,001, and that's still a solution. So we actually go all the way off to -infinity out here on the left. We got to be careful with that negative sign. Negative infinity is a different concept than positive infinity, or just what we would just call infinity. So we need to indicate that it's negative infinity. It is to the left of 7, so we are looking at -infinity to 7. And then we place parentheses or square brackets on our left and right sides in accordance with whether we want to include or not include that number or that idea. The infinity or negative infinity symbols always get an open parentheses. We never want to include infinity or negative infinity. They're not really numbers, so we don't actually include them in our solution set. We can't plug in negative infinity into our algebraic structure and see if it works. It just doesn't make sense to do that. It's not a number. It's not a thing that X is being a placeholder for. However, 7, on the other hand, we do want to include. So we put a square bracket there, and that's where we get our interval notation. So we kind of build our interval notation from inside out almost. We figure out what numbers or quantities we want to use, what order they should be in, which should be to the left of the other. And then we decide whether we want parentheses or brackets on either side. One little side note, I'm going to throw this in as an aside. Let me actually do it in red. I don't recommend doing this. There is a notation where if they want, A less than X less than B, something like that, then I want to indicate an interval that's strictly between two numbers. Instead of doing open parentheses A comma B, sometimes you'll see square brackets pointing the wrong way, like this or something. There's a notation that's out there like that. I strongly recommend against this. Number one, it's not a common notation. I've seen it in textbooks. I've said, I've seen it in some textbooks before, but I would strongly recommend against this. It's just, um, you know, I see why they do it. There is a reason that they do it. Um, you know, but I think it's just I think the costs far, far outweigh the benefits. Let's say it that way. So I don't recommend doing something like this for an open interval, writing brackets pointing the other direction. So I'll just leave it at that. I would not recommend that. So if you know that that notation, or if that's, if you learned that somewhere along the line, or if you see that pop up, if you're looking at another resource, I would not use that notation. But I just want to point that out. Does it matter which way I write the number within the parentheses or brackets? So if you mean the negative infinity and the 7, yes, it does. By convention, we always want to write the smaller number to the left. Or if we have a negative infinity, that always goes to the left. And the bigger number to the right, or if we have a positive infinity, that always goes to the right. So, you know, that's a notational convention. So if I wrote, open parentheses 3 to 7, I mean, if I had written open parentheses 7 to 3, if you were thinking more like a linguist, could we work out what is meant here? Yeah, probably. It's probably all of the numbers between 7 and 3. Is, we're just uh, we're just saying it a little bit differently. But this would just be considered bad notation. It would be considered an incorrect answer on WebAssign, and I think just about any math faculty would mark it wrong as an incorrect answer. So a lot of math is about notation and using notation properly and carefully, and we would consider this incorrect. Could you make an argument that, in essence, like, we're discussing a grammar here, a prescriptive way to use symbols to communicate ideas? Could you make a linguistic argument that, well, if I wrote it that way, the person on the other end probably would understand what I'm saying? Yeah, probably. But they would also probably be kind of confused. So if nothing else, it would make it difficult and more challenging to read or interpret, even if the person could eventually work out what it means. So it is important that the smaller number goes to the left, the large number goes to the right, or if we have a negative infinity, that it goes to the left, positive infinity to the right. Okay, and then our next exercise, since I spent a decent bit of time talking about the first, let's go quickly through the second. Here, our boundary is 4/3, separating the solutions from the non-solutions. X bigger than 4/3. We see that numbers like 2 or 3, something like that, are solutions, where numbers like, say, 0 are not solutions. But also the boundary point 4/3 itself is not a solution. It is not strictly bigger than itself. So I indicate 4/3 on a number line, and I put either an open dot or a parentheses. How do you know where to put 4/3? So that that's prerequisite material. I'd recommend taking a look back in in either chapter 1 or at so OpenStax has a textbook that's before ours for more detail. But the kind of crash course is that I know that 4/3 is between 3/3 and 6/3, or in other words, it's between 1 and 2. So I know it's going to be between 1 and 2. I mean, was my 4/3 up here? It probably wasn't quite close enough to 1, but this is our graphs are never going to be perfect. I wouldn't want, to put my 4/3 like on top of 1. I wouldn't want to put it on top of 2. I probably wouldn't want to put it like way over towards 2. But kind of if it's closer to 1 than 2, then I'm good. I know that it goes 3/3, 4/3, 5/3, 6/3. So I know that 4/3 and 5/3 have to equally split the distance between 1 and 2. So being a little closer to 1, that's what I'd be looking for here. So there are some problems on WebAssign that are like, drag these dots to the right place in the number line. I think they might have been in the chapter 1 kind of review material. And that's basically what WebAssign is looking for is, if a number is supposed to be on a tick mark, is it right on that tick mark? Or if it's supposed to be between 2 tick marks, is it between those 2 tick marks? That's basically what it's looking for. And that's what I'm more or less doing here. So I know that 4/3 will be between 1 and 2, a little closer to 1 than to 2. And that's about as refined as I'm getting here. But yeah, I mean, it's a good question that like, how accurate, how much time do you spend drawing these graphs? How accurate do you want them? Um, that is a little bit of um, a subjective question, right? We could spend more time like making our 0, 1, and 2 nicely equally spaced, and then between 1 and 2 making two tick marks that are pretty close to equally spaced. And then I know that the one on the left of those is 4/3. Um, but I don't see a whole lot of benefit to doing that in a situation like this. Now, if I was drawing a graph, like maybe later on in the course, when we look at systems of equations, looking at graphical solutions of those, if I was drawing a graph of these two equations by hand and trying to use the intersection of that graph to guess what the solution is, and then I might want to actually take an extra couple minutes and draw my graph more accurately because I'm going to be using that for another step. This graph is kind of an endpoint in the sense that like there's the graph of the solution, I'm done with it at that point. But if I was maybe going to be using the graph to help me figure something else out or to make a guess at what a solution might be, something like that, I might want to take a little more time and draw it a little more precisely and a little more carefully. So that does bring up a good point of, you know, there's some subjectivity here in how accurate do we want things. And I would say as long as things are kind of roughly in between the correct tick marks, that's close enough. That's as an aside, that's also why we label things because, I know that my line is certainly not going to be perfectly at 4/3 because pixels aren't, 0 width wide and I'm not infinitely precise in my drawing. So I label it as 4/3. In again, we have our interval 4/3 to infinity. There's infinity off to the right there. Here's 4/3. I do not want to include 4/3 because of the strict inequality. And I also put a parentheses on infinity, and that's my interval notation. Any questions so far? Okay, so what if we have an inequality like this one where it's not in a situation where we've already isolated the variable. All of these ones we've dealt with so far had the variable isolated. I basically had my scales. I had X on one side and I had some amount of stuff on the other side, and I told you which way the scales were supposed to tilt. Well, this gave me direct information about X. But if I have X minus 1, or let's make it a little easier, X plus 1, so I can just put a block there on one side, how big should X be to make the scales tilt the correct way? Well, that's not readily obvious. So I have an algebraic structure here, X minus 1 greater than 2, but I wouldn't really call this an algebraic solution, right? It's not so simple that I can just observe and tell whether a number is a solution. I would have to do some work. Is X equals 1 or X equals 5 a solution here? I would have to simplify. I have to plug in, simplify, and then check. It's not readily obvious. So I want to do what I did when I said I want to solve the equation. I want to isolate the variable is the goal. I want to get X bigger than, less than, bigger than or equal to, less than or equal to some number. Now, one thing to note is that when I have a certain type of inequality, in this case, a strict inequality popping up in an inequality. So when I have a sign that is a strict inequality popping up in a statement of the type that is an inequality, so using the same word inequality in two different ways there. When I do some manipulations, the strict inequality stays strict. So a greater than with the types of manipulations we're going to do is never going to turn into a greater than or equal to later on. However, it should be noted that a greater than could kind of turn into a less than. What do I mean by that? Well, I mean that x greater than 2, well, let me not use 2. Let's say x greater than, 7. That's the same thing as saying 7 is less than x, right? These are really just the same statement. I have some equation solving steps that I had used to solve linear equations. Those same steps essentially all apply here in mostly the same way. So in other words, if A equals B, then B equals A. I can flip my equation around if it's more convenient for me to write it that way. Or in other words, I can rewrite A less than B as B bigger than A. I can swap everything around, but if I swap things around, the inequality has to point the other direction because the relationship between B and A hasn't changed. But I'm never gonna, have x bigger than 7 somehow turn into something with a less than or equal to. At least not in this context. Another thing that I could do is I could add a certain amount to both sides. If I have my scales up here, and if I say that if I, take x and add 1 block, that's got to be heavier than all of this material on the right-hand side. Well, if for a certain x, if that's true, if I add 3 red blocks to the left side and 3 red blocks to the right side, and I put that same value of x on that left side, the left side's still going to be heavier. That 3 blocks on either side balances out. I can add the same thing to both sides of an equation, or for that matter, subtract from both sides of an of an inequality, the same way I can for an equation. So I had an addition and subtraction property of equations. That was an equation solving step. I can add or subtract the same thing to both sides. I have the same property for inequalities, that I can add or subtract the same thing to both sides of an inequality, and the resulting inequality will be equivalent to the original. So in other words, I see that I have my variable here, x, but it has a -1 attached to it. If I add 1 to the left-hand side, so long as I add 1 to the right-hand side as well, I end up with, on the left-hand side, x minus 1 plus 1 is just x, bigger than, inequality still points the same way. There's kind of a saying that, the inequality is like a crocodile and it always eats the bigger thing. It's like a crocodile mouth and it eats the bigger quantity. So if that helps you remember it, up here, the crocodile is eating the side with the x on it, and down here it is as well. And on the right side, 2 plus 1 is 3. So by adding 1 to both sides of my inequality, by putting 1 unit of weight on the left side and 1 unit of weight on the right side, we come up with another inequality, and this is equivalent to the first one. All of the x's that satisfy the second inequality will satisfy the first, and all of the x's that don't satisfy the second inequality will not satisfy the first. But we actually see that this is essentially a solution, right? This is an algebraic solution, x bigger than 3. So I can apply essentially an equation solving step, but here we might call it an inequality solving step, by adding 1 to both sides, getting x bigger than 3. Now it's in a form that is trivial to inspect, right? If I say is x equals 5 a solution? Well, yeah, it is, because 5 is bigger than 3. Is x equals 1 a solution? No, because 1 is not bigger than 3. Is x equals 3 a solution? No, because 3 is not strictly bigger than 3. Kind of by default, when we say to solve an inequality in a course like this, we mean to represent it in all 3 different ways. So I'm also going to represent this graphically. Here's 0. Here's 3. I want x bigger than 3, so I'm going off to the right. And since it's a strict inequality, maybe I'll put an open dot here. I could have just as well used an open parentheses opening to the right. That would have been fine too. But I'll leave this as my graphical representation. And I do see, if I wanted to check, I see that 5 is to the right. Is 5 bigger than 3? Yes, it is. I see that maybe 0 is to the left, and my graph suggests that 0 is not a solution. Is 0 bigger than 3? No, it's not. So it does seem like my graph is in line with my algebraic solution. We have to keep the sign. So we'll end up with whatever sign we end up with. In this case, because we added 1 and we started with a positive number, we did end up with a positive number. But I could have had, let's say, for instance, x minus 3 bigger than -2. If I add 3 to both sides, I'd have x bigger than 1. So I think the sign could change if that's what you're asking, but it would just depend on how the arithmetic works out when we do the simplification. Unless I misunderstood what you're asking. But yeah, so I mean, the sign that we end up with is just a result of, however the arithmetic shakes out when we simplify things. And then our interval notation, starting here at 3, going off to positive infinity. So we're going from 3 to infinity. The 3 should be on the left, the infinity should be on the right. I want an open parentheses around the infinity because the infinities always get open parentheses. We're not actually including that infinity as like a number that's a solution. And I note that I have a strict inequality, so I do not want to include 3 either. 3 is not strictly bigger than 3, so I want an open parentheses here as well. So this is my graphical solution and my interval notation representation of the solution. And these different versions of the solution are nice in different aspects. There are sometimes when having one is beneficial to the other one. So that's why we kind of write all 3. Gets us practice dealing with them all. Now, what about this inequality? 5x is less than or equal to 10. Again, I think of like I have my scales over here. And let me draw them a little bigger, a little better than before. And I got them kind of going the wrong direction. So here I have 5x, which I'll draw as just like a blue square to represent envelopes. Less than or equal to 10, which I'll just draw as like 10 little spheres. So each of these little blue envelopes, I don't know what is in them, but I know that when I have 5 of those, they weigh less than 10 of these red spheres that say weigh 1 unit of mass each. I just offended all of the physics and chemistry folks by saying they weigh a unit of mass, but that's why I like math. I don't have to worry about units. But I know that if 5 of these same envelopes weigh less than 10 of these red units, well, then it's got to be true that, say, a single envelope weighs less than 2 of these red units, because that same relationship has to work 5 times consecutively, right? I can divide both sides of my inequality by 5, just like with my equations. My equation solving step, if I have isolated my variable term, I look to isolate the variable by dividing by the coefficient. I divide by 5. 5x over 5 gives me x less than or equal to 10 over 5 gives me 2, right? Each of my envelopes has to contain mass less than or equal to 2 units of red mass in order for this scales to end up this way. That's an algebraic representation of the solution. I could represent it graphically, x less than or equal to 2. So I want to include 2. I guess I'll use a bracket here. Could use a closed dot as well. And my arrow going off to the left, going off towards negative infinity. Or an interval notation solution, I see I'm going from negative infinity up to 2. I do want to include 2, so I use a square bracket on 2. And of course, I don't include negative infinity, so I use an open parentheses there. So I see that applying my same equation solving steps, but to inequalities, at least up till now, there's a little catch, but at least up till now, works just fine. I can add or subtract the same number to both sides of the inequality, and I maintain an inequality with the same solutions as the original one. I can divide, at least as of right now, both sides of the inequality by a number, and I maintain an inequality that is the same as that has the same solutions as the original one, and my alligator is still chomping the right-hand side away from the x. Let's take a look at these two exercises and work through these. So apply the equivalent of an equation solving step, adding or subtracting something from both sides, dividing by a coefficient, something like that. Apply that to these inequalities to get an algebraic solution, and then write that algebraic solution in a graphical representation and an interval notation representation. So we'll come back in maybe about 4 minutes or so and work through these two exercises. Okay, let's touch base on these two exercises. I need to look up how to get OneNote to stop doing the scribble to erase thing. I think they added that feature in, and now when I try to fill in my dots, it like fills it in and then erases it. Um, okay, so solving this first inequality, just like above, we have a variable term and a constant term on one side of the inequality in this case. So I want to isolate the variable term. I do that by subtracting 3 from both sides, giving me x less than 1. And that's an algebraic solution. I can graph x less than 1 like this, my arrow pointing to the left of 1 with an open dot or perhaps an open parentheses at 1. That's my graphical solution. My interval solution going from negative infinity up to 1, open parentheses on both sides, the open parentheses on the right, indicating the strict inequality, and the one on the left indicating that we never really include the infinity or negative infinity. And then for the second, we divide both sides by 7. We have the variable term isolated, but we need to isolate the variable itself. Dividing by 7 accomplishes that. Negative 28 over 7 is negative 4. X bigger than or equal to negative 4 is my algebraic solution. My graphical solution, say, for instance, a filled in dot at negative 4 with the arrow pointing to the right, or perhaps a square bracket at negative 4, arrow pointing to the right. And I see my interval is negative 4 to infinity. Open parentheses infinity because we never include the infinity or negative infinity. Close bracket at negative 4, indicating the non-strict inequality that it's x greater than or equal to negative 4. So negative 4 itself is a valid solution because negative 4 is equal to negative 4, so it's of course greater than or equal to negative 4. Any questions on these ones? Okay, now down here, let's take a look at this inequality. Sorry, my allergies have been just going haywire this week. So let's take a look at this next inequality. And here, given our previous success with applying equation solving steps, we might just jump into this and say, okay, negative 5x less than negative 10. Divide both sides by negative 5 and get x less than negative 10 over negative 5 is 2. Does this work? Let's try to solve this a different way. So I know that I'm allowed to add things to both sides of an inequality. That's really clear, I think, um, based on the example up here, that adding the same amount to both sides of an inequality is not going to change that relationship. If the left side is less than the right side, if I add 5 to the left side and add 5 to the right side, the left side's still going to be less than the right side. So I have negative 5x less than negative 10. I could add 5x to both sides if I wanted to. And I would get 0 less than negative 10 plus 5x. And I suppose if I wanted to, I could add 10 to both sides. And I would have 5x on the right and 10 on the left. So 10 less than 5x. Now I can apply my equation solving step, divide by 5. And on the left side, I get a 2. On the right side, I get an x. But now it's 2 less than x or x bigger than 2. Wait, I got two different answers here. What's happening here? Let's take an aside and look at what's happening. Let me consider a number line. And let me look at it, maybe an interval, say 1 to 2. I use blue. It doesn't much matter if this is an open or closed interval, but this is the interval 1, comma 2. Right? So I see that 2 is to the right of 1, for instance. If I add a number to this, if I say add 1 to it or subtract 1 from it, what am I doing? I'm moving this interval to the right or to the left. It's just shifting the interval. If I add 1 to both bits, let me give myself a little more room here. Now let me add 2 so that it's a different interval. 1 plus 2 is 3, 2 plus 2 is 4. 1 goes to the 3, 2 goes to the 4. They kind of stay in the same order, right? My lower number, maybe I'll circle, goes to the lower number, and maybe I'll put a diamond around the bigger one, goes to the bigger one. So this is if I add a number. If I subtract a number, it does the same thing. We're just taking this interval and shifting it right or left. No orders are changing or anything like that. If I multiply by, let me draw the same interval. I have my interval 1 to 2, and I multiply, let's say, by 3, then 1 turns into 3, and 2 turns into 6. I have this interval 3 to 6. My interval gets wider. From 3 to 6 is 3. And as my interval gets 3 times as wide, but I still notice that my lower number goes to my lower number. My bigger number goes to my bigger number. What happens if, say, let me draw my interval again. I know that these are taking a little while to draw, but I want to give you the visual representation of what's going on here. What happens if, say, I take, again, my original interval, say from 1 to 2, and what if I multiply by, say, -2? Well, then 1 multiplied by -2 1 goes to negative 2, and 2 goes to -4. Jeez, I gotta turn this off. I see now I'm looking at the interval from -2 to -4. But I noticed that 1, the number that started out as the lower number, now is the rightmost number. It's the higher number. The number that was at the left end of the blue interval becomes the right end of the green interval. And the number that was the higher number initially, the right end of the blue interval, comes over to the lower end, the left end of the green interval. The order switches. Why is that? Well, when I multiply by a negative number, basically what I'm doing is I'm kind of flipping about the 0 axis. Positive numbers flip over to negative numbers flip over to positive numbers, but also a direction, like say pointing to the right, when I flip it over, my direction changes and points to the left. Or my inequalities change. Or if I look at something like, let's consider just like x greater than or equal to 2, and then I multiply by, let's just say -1 on both sides. Well, when I multiply by -1, my 2 flips over here to a -2, because basically what I'm doing is I'm taking this axis and just flipping everything about it when I multiply by -1. So the +2 flips to a -2, but my arrow pointing to the right becomes an arrow pointing to the left. And since I multiplied both sides by -1, I have that -x is now related to -2. How? By being less than or equal to. So my equation solving steps almost just come over into inequalities with no changes. But there's one detail that when I'm multiplying or dividing by a negative number on both sides of an inequality, oh, I have to switch the sign. So -5x over 5 gives me x. That's fine. -10 over -5 gives me 2. That's fine. But my inequality has to switch directions. Instead of facing to the left, instead of the less than the smaller side facing to the left towards x, the smaller side now faces away from x. I would recommend when you do one of these steps where you're multiplying or dividing, especially by a negative number in inequalities, keep your sides the same for that step. So keep the -5x turns into x. I keep that on the left. The -10 turns into a 2. I keep that on the right. And then I switch the direction of the inequality. And then if you want to switch which side what's on, like I did here, do that in a separate step if you want to do that at the end to make it look a little nicer. But I noticed that if I add the rule that if I multiply or divide by a negative number on both sides of an inequality, if I flip the sign as well, then I get concordance between the situation where if I kind of added stuff to both sides to get a positive coefficient and then divide, that gives me x bigger than 2. Or if I just did the division straight away, that gives me x bigger than 2 now. Now they agree. What does this kind of mean in the scales? Well, if we were to think of, let's say, money, for instance, right? Like if I have more money in my pocket than you have in your pocket, then I have more money than you. But if a malicious genie came along and changed all of the money we have in our pockets to debt that we owe somebody else, well, now I have more debt than you have. I owe more than you, so I have less money than you have, right? If I switch the sign, it's kind of like changing assets to debts. Or it's kind of like saying instead of mass, these red guys being mass pushing down and these blue envelopes containing mass that pushes down. It's almost like they're now an amount of helium like pulling up, right? They're moving in the opposite direction. So if I had more red things than stuff was in the blue envelopes when I'm thinking of mass, that pulls the right-hand side down. But if I'm thinking of helium, if I like negate that, if it goes the opposite direction, it's kind of the right side is pushing up harder than the left side is pushing up, and now the inequality goes the other way. So if I multiply by a negative, if I do that inequality solving step, I've got to change the sign. It would be super nice if I didn't have to change the sign at all, right? If I just ended up with a positive coefficient. And that was why in the equation solving steps in the previous sections, I kind of harped on the idea that, well, when we get our variable terms together, it's nice to get a positive coefficient. This way, if we have a positive coefficient, we don't even need to think about changing the direction of the inequality. We just go ahead and apply the inequality solving step, and the inequality stays the same direction. Up here, we had a positive number we divided by, so we didn't need to change the direction. So if I can engineer a situation where I end up with a positive coefficient for x, that just saves me, from encountering another source of error. So if I have a choice, if I have a choice of which side to put my variable terms on, I'm going to choose the side with the positive coefficient that gives me a positive coefficient. Just one less thing to think about, one less place to make a mistake. Um, there was one more thing. Oh, why don't we need to do something with an equals? Why doesn't dividing by a negative mess things up with an equals? Well, because with an equals, they're exactly the same, right? If I have exactly the same amount of money in my pocket that you have, and then the malevolent genie comes along and switches it to debt, well, now still have exactly the same amount of debt as you have. They're still equal. Or if the mass in the envelopes is exactly the same as the mass in the red things when they're pushing down, if I switch them to helium, they push up, they're still pushing up at exactly the same amount. So with an equal sign, we don't have to make any strange adjustments because the two are exactly the same, whether they're on the left or the right side of the number line of zero, or whether they're like helium or mass, or whether it's assets or debt. It doesn't really matter. They're exactly the same either way. But once we start saying that one is bigger than another, when I hit that with a negative, then that kind of flip-flops the perspective. All right, so take a look at this exercise. This should probably only take a minute and a half or so to do, but solve this two ways. Do it one by adding 3x to both sides to get a positive coefficient, subtract 9 from both sides, and then divide by 3 and see what answer you get. And then do it by dividing by -3, being careful to flip the sign, make sure you get the same answer. So take a minute or so and work through this one, and we'll come back and write down the answer. All right. Sometimes I love the AI thing on Google. I just Googled really quickly, like how to make the scribble to erase stop in OneNote, and it was like, yeah, go to this menu item and uncheck this box. And I don't know if you were able to see when I did that or not, but I jumped in and fixed it. So sometimes AI is great, and sometimes it, gives you a picture with feet for hands or something. Uh, but anyway, so solving the inequality two ways. We can add 3x to both sides, getting 0 bigger than 9 plus 3x. Subtract 9 from both sides, giving -9 bigger than 3x. Now we have a positive coefficient. We divide by 3, and we get -3 bigger than x, or we can rewrite that as x less than -3 if we prefer. A lot of times it's just nice to have the x on the left. We're just a little more used uh, to looking at and parsing information that way. Or I could just directly divide by -3. That saves me some steps. That's really nice. But I have to do this all-important step of switching the inequality. So on the left, I have x. On the right, I have 9 over -3 is -3. But the inequality originally pointed to the right. So the smaller side was to the right. And now the smaller side points to the left. So x less than -3. We do get concordance between the two methods, so long as we're careful with switching the inequality direction when we divide by the negative. Any questions so far? All right, let's look at a more challenging problem then. So here I want to solve this inequality, and this is a pretty complicated one, right? It's got a lot going on. Now, the nice thing about inequalities is, well, we went through, what was it, 6 sections or so of solving linear equations and building up to a general solution method for linear equations. The same solution method with the minor detail of that I mentioned before of switching the sign when multiplying and dividing by a negative, but the same strategy, the same solution methods and everything work for inequalities. So here I have a linear inequality. I have an expression on the left that can be simplified. I have some constant terms and some variable terms. And my goal is going to be to simplify to get ax plus b related to cx plus d, whether that's bigger than, less than, bigger than or equal to, less than or equal to, whatever relation I have. But on each side, I want the expression, on each side of the inequality, I want the expression to just be one variable term and one constant term. And then I can work on combining the variable terms together, isolating the variable term, isolating the variable itself, and writing out my solutions. It's the same strategy. And essentially exactly the same steps with that one caveat, multiplying by a negative. So what's the first thing that I'm going to do here? Well, the first thing I'm going to do is simplify. On the left side, I have 7x. I need to distribute my 5. So plus 5x minus 15, bigger than or equal to -10x plus 12. And then I combine like terms to give me 12x minus 15, bigger than or equal to -10x plus 12. I'm now in my kind of standard form. I've completed step 1, simplifying both sides, both of the two expressions, both sides of my inequality. But now again, I have my variable popping up twice. I have 2 different variable terms. I want to get my variable terms together. I could choose to add 10x to both sides and get my variable term on the left, or subtract 12x from both sides and get my variable term on the right. If I were to subtract 12x, that's going to give me a -22x. And looking ahead, I strategize a little bit. I say, wait, that means I'm going to need to divide by a negative. I'm going to need to remember to switch my sign. I would rather go the other way. Just a little less error prone, a little less to remember. I'm going to add 10x to both sides. That gives me a 22x on the left. My inequality stays the same direction. If I'm adding or subtracting from both sides, the inequality stays the same, even if I'm subtracting, right? Think of your scales up here. If I, get rid of 2 red blobs over here and I get rid of whatever 1 envelope, the scales still balance in the same way. I mean, we saw up here that the envelope kind of contained like 2 blobs, or even better, if I had these envelopes plus 2 blobs. If I get rid of these 2 blobs and those 2 blobs, the scale still balanced the same way. So note that if I'm subtracting a number from both sides, really all that's doing pictorially, adding or subtracting a number, is just shifting my interval left or right. Nothing has flip-flopped. It's just moving left or right. So adding or subtracting from both sides, like in this case, whoops, forgot to write down my other expression. Adding or subtracting from both sides doesn't change the inequality. So inequality comes down just as it is. On the right side, I have 12. I have my variable terms combined together. I want to isolate the variable term. I do that by getting this minus 15 to the other side by adding 15 to both sides. 12 plus 15 is 27. So now I have 22x bigger than or equal to 27. I've isolated my variable term. I want to isolate the variable itself by dividing by the coefficient. And because I planned ahead, the thing I'm dividing by now is positive. My inequality stays the same direction. I see that 22 has factors of 2 and 11. 27 is 3 cubed. No common factors to divide out. That's my answer. That's my algebraic solution. I know that 27 20-seconds is 1 and 5 20-seconds. So a little bit to the right of 1. This is bigger than or equal to. I suppose I'll put a filled in dot there, going off to the right. So 27 20-seconds, going off to infinity. I could represent my solution graphically that way, or as 27 20-seconds to infinity. Never include infinity, but we do want to include 27 20-seconds. Any questions on that one? Okay, so we're right on time today. So take about 3 minutes or so, solve this exercise. We'll come back, talk through the answer, and wrap up for today. So 3 minutes or so to solve this one. All right, it's just about 3 minutes, so let's talk about this one. There were a couple places in this one that you could have, gotten a little bit tripped up with a question of, wait, do I change the inequality or not? And if you took this approach, you don't change the inequality at all the whole time. So what do we have? We have distributing the 3 into the x plus 1 first. We have 8x plus 3x plus 3 less than or equal to negative 3x plus 1. That gives us 11x plus 3 less than or equal to negative 3x plus 1. We're in standard form. So we've completed step 1. Now we have more than one variable term, so we combine our variable terms. And again, I choose to do that in the direction that gives me the positive coefficient. So I choose to add 3x to both sides. It's not incorrect if you were to subtract 11x from both sides, but then you just have to, a couple steps later, remember that you're dividing by a negative number, make sure to switch the sign. But here, I'll choose to add 3x to both sides to get 14x plus 3 less than or equal to 1. I've combined my variable terms together. I want to isolate the variable term by getting rid of this plus 3. I do that by subtracting 3 from both sides. Note that I'm subtracting here, not dividing by a negative, in which case I would have to switch the inequality, but I'm subtracting. I'm just basically taking that interval and shifting it left. But the bigger number kind of stays the bigger number, the smaller number stays the smaller number, even when I shift to the left. So just subtracting here, I don't switch the inequality. So it's still 14x less than or equal to negative 2. I subtracted a number, don't shift the inequality. And also, just because I got a negative number on the right, as a result, when I did my subtraction, that also doesn't impact the inequality at all. So don't get tripped up and think that there are too many situations where you need to switch the inequality. It's only when you're multiplying or dividing by a negative number. If we're adding or subtracting a number or adding a negative number, anything like that, then we keep the inequality the same. Now I have 14x less than or equal to negative 2, divide by 14 to isolate the variable itself, divide by the coefficient. We're dividing by a positive number, so we keep the inequality the same direction, x less than or equal to negative 2 over 14, which simplifies to negative 1 over 7. And we could write that answer graphically or in interval notation in either of these two ways. Now, an exercise for next time. What if I had 8x plus 3 times x plus 1 less than or equal to, if instead of negative 3x here, what if I actually had 11x? This is going to be one of those kind of strange situations we saw in equations where all of my x's go away, right? I'm going to get 11x on the left side, 11x on the right side. And when I try to combine those two variable terms, I'm going to get 11x minus 11x. My variables are all going to go away. Try to reason through this on your own. You can look in the book and see what the answer is, and we'll go through some examples next time, but try to reason through on your own. When these x's all go away, what is that maybe indicating to you? So give us a little bit of a thought for next time. And on Thursday, we'll pick up with the last bit of inequalities and the last bit of chapter 2. Let me stop the recording.